Dude, it's cool learning about Fourier analysis on inner product spaces, but dude, I really want to see the waves, and I want to get to the proof of Parseval's inequality. So, man, we could just have a grand old time, dude, like tubular. Yeah.
Yeah, that's very nice, Hermione. We're going to get to that just for you. The Parseval theorem. So first, the question is, prove that in any inner product space, F and G are orthogonal, implies that norm F squared plus norm G squared equals norm F plus G squared. Hey, it's like the Pythagorean theorem. Let's do the proof. All right, so who knows what we should do first? Should I calculate the left-hand side or the right-hand side? That's right, Fred. The second letter of Fred is R, so let's start on the right-hand side. Good reason. Good. All right, so here we go. So that's, the inner product of F plus G with itself. And we get, let's see, what should we use next? That's right, Slopey, the second letter of Slopey's an L, so we should use linearity. Good reason. I like that. So you use linearity, and it's basically FOIL, but you have to worry about the order of things because it's a complex inner product. So you have to kind of do it like this. Good, good. And guess what? If they're orthogonal, that's 0 and that's 0. So you get this. And wait, what's that you want to say, Hermione? That's right, the second letter of Hermione's E, for that's the end of the proof. That's right, because that's the same as that. Good job. All right, so now let's let's do the proof of Parseval's theorem. Okay, so remember what that was, is that you have a complete orthonormal basis if and only if the Fourier sums, which are these you have an orthonormal basis, and you want to look at the partial sum, which sum from k equals 1 to n of ck, fk, where ck is the inner product of f with fk, and you want to show that so the basis is complete if and only if for all f in v the difference between f and the partial sum goes to 0 as n goes to infinity. Right? Well, just remember from before is that we actually did some computations, and we can actually look at what this is. This is the same thing as f minus Sn with f minus Sn. And then remember, we showed that this part equals 0 from the Bessel calculation proof. We showed that that part equals 0. Great. And so you can actually write down what this is then. So this is f with f minus Sn with f. Okay. And let's see. So what is that? So it's a value of f with f minus, and we also calculated what this was. This is, since this is the summation of ck fk, this is the summation of ck times fk with f. Right? And what this is, and the ck, remember, is this. And so, we can put that next to each other. And remember, when you switch the two things, you get the complex conjugate. So you get ff, and this is up through n. Well, it's just ck bar, which is and this is exactly, so this goes to 0 if and only if this is the sum to infinity of that, right? Equals, because the partial sums get closer and closer to that. Yeah. And I'll actually put the QED. And that's exactly what Parseval's theorem is. It's great stuff, man. All right, so now I'd like to actually use some of this stuff. And just kind of do some computations. So on 4 point, now we're getting to the wave part. Woo! Yep. Are you excited about that? All right. So we're going to show in question 4 point, these are exercises from the book. In exercise 4.1.1, we're going to show that 1 over square root of 2 pi cosine nx over square root of pi and sine mx over square root of pi is an orthonormal sequence set where n and m are natural numbers, and L2 of closed interval negative pi to pi. So we just need to check the inner products of everything. So the proof of this will be, let's check the inner product of 1 to the square root of 2 pi with itself. So that's the integral from negative pi to pi of 1 over square root of 2 pi times its bar. Which is 1. Check. Good. And let's check the other guys too. How about cosine of nx over square root of pi? Cosine of nx over square root of pi. And so multiply together, those are both real, so it's just cosine squared of nx, and then 1 over pi over here, dx. And this is a standard calculation. Right? And then this integrates to 0, so it's just like integrating 1/2 and over 2 pi. So it's 1 pi times 1/2 times 2 pi, which is 1. Check. So far the inner product of all these things with themselves is 1, and we'll check the same thing with sine. Again, 1, same calculation, except you have sine squared, and that'd be 1 minus that. Yeah. All right. using the trig identity. Great, and now we need to check what about if this with that, this with that. So next, let's do the inner product of 1 over square root of 2 pi with cosine of nx over square root of pi. So that is, multiply those together, 1 over square root of 2 times pi, integral of cosine of nx dx from negative pi to pi. And that's just a way it'll have the same positive areas as negative areas, so it'll be 0. Check. Same thing if you do this one. Same thing will happen. All right, let's see, what else do we need to check? So we've got this one, that. Okay, now we need to check this one with that one, and this one with that one for different numbers, and this one with that one with different numbers. All right, so actually, we need to Google these formulas, but we need to find the formula for cosine of nx, sine of mx, and then we need to find the formula for cosine of nx, cosine of mx, and then we need to find the formula of cosine of mx, sine of kx. So for different numbers, we need to find the formula for what these things are. Okay, so let's quickly compute that. Well, actually, yeah, I mean, I could do it that way, but let's just let's see if this will work. Let's see. There we go. Yeah. So let's see, that one was this one right here. So this is the same thing as 1/2 of cosine n plus m x plus 1/2 cosine of n minus m x. And then let's change it to sine here. And same thing with the minus, it's with sine. That would be this one. So it's 1/2 sine of the sum okay. And then let's put 2 sines and see what happens. These are just trig identities, which you can verify. Cosines with the minus. So this would be 1/2 cosine of actually the minus first. Yeah, and so now as a result of that calculation, if you take the inner product of this with this, you'll always get 0 because that will integrate to 0. Those are both sinusoidals. And let's see, if you take the integral of that with another one like that, but with a different constant, you'll get 0. Same thing with that one, again, because of these formulas. And so really this is an orthonormal set. So, and later we'll actually prove the Rees-Fisher theorem that it's a complete orthonormal set. So it's pretty cool stuff.